Okay, I promised to do a video about the third buffer problem from the PowerPoints about the glycine buffer. We're told we have 1 liter of a glycine buffer that's at 0.1 molar concentration. That is at a pH of 10, and the pKa of glycine is 9.8. Okay. Now this is the description of the buffer that we're given, and then we're told that once we know that buffer, that we're going to insult it with the addition of a strong acid, and we're going to add 10 milliliters of 1 molar concentration of a strong acid. And the question is, what's the final pH after we treat this buffer with strong acid? Okay, the first question is this a buffer problem? And it is, because we've said buffer about 3 or 4 times already. It says buffer. We've got a glycine buffer, which is a weak acid and its conjugate base. Notice I didn't even write glycine here. It doesn't matter what the structure of glycine is or anything. We just need to know its dissociation constant, or its pKa here. So I'm going to write the Henderson-Hasselbalch equation first, because I know this is a buffer problem and I'm going to need to use it. And then I will try to fill in what I know and figure out what I don't know. The pH we know, it's 10. They tell us that. The pKa we know, it's 9.8. We do not know the concentration of base or the concentration of acid. And mathematically here we are stuck. Really, we've got 1 equation and 2 unknowns. We can't solve for both of these unknowns with this 1 equation. We need another equation. And although we aren't told the specific concentration of base or acid, we are told the total concentration of these components in the buffer. It's a 0.1 molar glycine buffer. What that means is that the concentration of base plus the concentration of acid equals 0.1 molar, and that's our second equation. So what I'm going to do is solve here for concentration of acid. Concentration of acid equals 0.1 molar minus concentration of base, and I can substitute this in, right? Whenever I see acid, I'm going to substitute in 0.1 molar minus base right here. And so I can be left with this equation. 10 equals 9.8 plus log of the concentration of base over, instead of concentration of acid, I know it's 0.1 molar minus concentration of base. Mathematically, I'm in good shape now. I've got 1 equation and 1 unknown, and I can solve for this, right? Let me bring the 9.8, subtract that from both sides to leave me 0.2 equals concentration of base over 0.1 minus concentration of base. Oop, I forgot the log there too. Now the log's a problem. How do I get rid of that log? Well, I raise both sides of the equation 10 to the x. 10 to the 0.2, 10 to the log, it gets rid of the log. 10 to the 0.2 power is 1.58, and that equals base over 0.1 minus concentration of base. I can cross multiply here, so 0.158 minus 1.58 times the concentration of base equals concentration of base. I'm going to move my base to one side, so I'll add 1.58 times concentration of base to both sides. 1.58 equals 1.58 plus 1, this is 1 base, so we have 2.58 times concentration of base divide both sides by 2.58, and I end up with concentration of base is equal to 0.0612 molar. Okay. Now, since I know that the concentration of base plus concentration of acid equals 0.1 molar, I can just plug the base in here. And I will know that the concentration of acid, therefore of my original buffer, equals 0.0388 molar. Okay. So I have described the original buffer according to Henderson-Hasselbalch completely. I don't have any unknowns left. I can say that the pH is 10, the pKa is 9.8, the concentration of base is 0.0612, the concentration of acid 0.0388. That makes a little bit of sense. Since the pKa is 9.8, if I want the pH to be a little higher than that, then I better have more base than acid. Okay. Now really this is only half the problem. We still have the problem where we are going to treat this buffer with 10 mils of a 1 molar strong acid solution. And so one clue to make these problems easier is to still use the Henderson-Hasselbalch equation, but instead of concentrations here, we're going to turn these into moles. And the reason why is because the way I think of buffers is that for every mole or every molecule of strong acid that we add, we're going to alter the concentrations or the number of molecules of base and acid in a way that makes a little bit of sense. And so I'm going to try to write out the Henderson-Hasselbalch equation for my buffer after the addition of this amount of strong acid. The new pH is unknown. It's going to change. It's probably going to go down some. The pKa is the same. The concentration of base and acid are going to change, but they're going to start off, whoop, I forgot a 0 there, 0.0388. Now, I'm going to treat these as moles because I know I have 1 liter. 1 liter of a 0.0612 molar solution has 0.0612 moles in it. Okay. Now, how can I adjust the base and acid to reflect the strong acid that I've added? Well, I know I'm adding 10 milliliters of a 1 molar solution, and so I have 0.01 liters times 1 mole per liter. I am adding 0.010 moles of strong acid. Now, what is that strong acid going to do? Well, it's going to react with the weak base and convert it to the weak acid. So for every mole of strong acid I add, I'm going to subtract that many moles of base, and I'm going to add the corresponding number of moles of acid. Okay. So really what I end up with here is saying pH equals 9.8 plus log of 0.0512 over 0.0488. I have reacted some base and converted it to acid, changing this ratio, and it's going to change the overall pH of the solution. Okay. So if I do some math on this, I'll find that the log of this ratio is equal to 0.0212, and so the final pH of my solution is equal to 9.82. Does that make sense? Well, I've added some acid to my buffer. My buffer changed from a pH of 10 to a pH of 9.82. So that makes a little bit of sense.